The subject of this Module 4 video, epoxides, comes pretty logically after we've examined all the different nucleophilic additions to carbonyl groups, but we'll see that epoxides add additional versatility and are interestingly similar to carbonyl groups. We're focusing most recently on carbon nucleophiles and noting that we can create an alcohol. Alcohols matter because you can derivatize them into better leaving groups, for example. You can make a tosylate, we saw before. You can do all kinds of reaction chemistry further on alcohols. So look at our carbon nucleophile, the Grignard reagent, like we've seen in our last unit. This can attack a carbonyl group, like a ketone here. We've done this. Picks up a proton from water, and notice the point of attachment at this carbon. So the carbon bearing the alcohol is also the carbon to which the carbon nucleophile is attached. And of course, these two carbons here end up being these two carbons here with the new bond shown in green. So that's where we have left off. Now epoxides, structurally, really they're cyclic ethers. If you look at it closely, this would be the simplest possible epoxide. It also has inductive effects. So it's polarized because of the oxygen, but it's also got a lot of ring strain. You may be surprised even to see a three-membered ring, but they can form. It's really good to try to build the models of these if your models allow it, but if it's not the right type of model, you might break them, so be careful. They have to have this sort of bendy bonds. So we have ring strain and inductive effects, so therefore these rings can be easily opened. A nucleophile can come in toward the delta plus carbon, break this bond, so bond forming, bond breaking. You see the new bond that's formed here. The oxygen stays attached to this other carbon, notice, and then it picks up a hydrogen. So our point of attachment of the nucleophile is adjacent to the carbon bearing the alcohol. That adds a lot of versatility, adds to our toolbox, our repertoire of reactions for making different kinds of organic compounds. So epoxides almost always have chirality, and then it would be, I think, impossible to see an epoxide where one of these bonds is forward and the other back. I don't think, I could be wrong. If there are rare examples of that, I'm not sure. So they're almost always on the same face for obvious reasons, and therefore they have chirality. Of course, depending on what's attached, I guess usually, but priority groups here, if you take a look, oxygen, if we're looking at this carbon here, oxygen is 1. Then you look over here, carbon, that carbon's got an oxygen on it too. It doesn't matter that it's the same oxygen. That's group 2, group 3, and group 4. As we're looking at it, 1 to 2 to 3 clockwise, so it's R. And so we have the RS version, and then if we put the epoxide facing back, notice we get the SR version. You can verify that. So this is really critical. Nobel Prizes, plural, have been awarded for the ability to make one of these selectively, with stereo specificity, we would say. And so that has been done really with pretty high efficiency. Here's an example of why that comes into play as important. If you use a ring system compared to like the very first example above, here's a Grignard reagent, here's our carbon nucleophile, we're adding a 2-carbon piece to this. It's going to come in from behind and realize this is basically an SN2 reaction. Nucleophile coming in to the other face opposite the leaving group, which is really not leaving entirely, but it's breaking this bond here, right? The hydrogen's going to invert. And what is the stereochemistry here? Configuration, I should say. 1, 2, 3. This is R. 1, 2, 3. This is S. Okay, so keep track of that. Bond forming, bond breaking, and then we have our new bond then that's formed here. We've added this 2 carbon piece, right? The hydrogen has inverted. Inversion. And notice the oxygen has stayed forward. In other words, retention at that position. And let's verify that. We can say groups 1, 2, 3. That's clockwise, but hydrogen's pointing toward us. So it's inverted now. It's S instead of R. This, however, remains S. 1, 2, 3. Counterclockwise S. I drew this out. We've seen this a bunch of times, but just nothing wrong with reinforcing it at this late date, I suppose. Notice the electrons on oxygen. Another lone pair is gained. There's 3 lone pairs here. When we add water in these reactions, to finish it off, we just protonate is what it's for. Following those arrows, you get the alcohol. So, inversion at the site where the nucleophile is added, retention because the oxygen just sort of swings over. So it's easy to see why those Nobel Prizes were awarded, maybe, because imagine an important drug-like compound. The stereochemistry at these positions is critical. As we know, some drugs are drugs if it's the right chirality, poisons if it's the wrong chirality. So the other thing is, filling in the final piece of all this, really we can plug in any nucleophile that we've seen to date here. So you can imagine any of our nucleophiles that we've used, oxygen nucleophiles, nitrogen nucleophiles, sulfur nucleophiles, so on. Maybe something like this. It's plug and play. Knowing and understanding one reaction like this and the mechanism allows us really to not have to memorize, but now we know hundreds or thousands of reactions, literally. Okay, so there's a final note, and you'll see this in your reading as well. You can catalyze this, in other words, speed it up. If you take a look, here's a nucleophile. Sure, this reaction can happen for reasons that we showed above, so it's reactive. But, especially in the case of a non-charged nucleophile like this, we can protonate first with acid. We get this activated oxygen, basically. And the nucleophile can come in, same mechanism. But notice these electrons are going to want to even go to the oxygen more now because they're going toward a full positive charge, which certainly is the direction they want to go. So that's even more reactive. It's catalyzed, it's speeded up. The energy of, well, you have an intermediate form, but then that ultimately lowers the energy of activation of the nucleophilic attack. Should remind you very much of what we've seen before. Really, it's identical, isn't it? Take a look at that. It's really identical to what we saw before. Yes, this can happen, but OH is a bad leaving group. But if we protonate the OH, saw this many times, great leaving group. Really notice how the principles keep repeating now. If you have a good grasp of the fundamentals, the remaining new concepts get easier and easier. The Klein reading is vastly better here. Some good problems there. McMurray, those particular sections.